Right, hello. This is the next instalment in the in the physics world. No, unfortunately, I'm not yet the director for physics world. That's tomorrow's job. What I thought we'd get cracking. So this is quite a short video today. It's not a long one. You'll be pleased to hear. The next topic we're going to do is all about single slit diffraction. Didn't say silt, it's slit. Yes, I just said it right. Sorry, got a bit excited there. I've never said it right before. And I still managed to mess it up by trying to explain how I did it wrong. So, what we've got is, diffraction. This is quite a basic physics term, so I will just demonstrate it with a simple GCSE wave analogy. So you've got the, I don't know if you can see it on there. Yeah, you can. So the wider the shorter the gap, the bigger the diffraction, and the larger the wavelength, the bigger the diffraction as well. That's just two basic things to help me to get to grips with the single slit diffraction somehow. Just thought I'd introduce you to it. You were just popped on this video and thought, you know what, I'll try a bit of AS physics. Alright, okay. So we've got the single slit, which is what I've just said. It's much like the Young's double slit, which we'll come on to in the next video if you're watching it the way I did it. So you've got a light box here. And it's high tech light bulb and a great big circle thing. Plug stuff in. Don't turn that into anything other than things to do with physics. So you've got a light coming through here. This is a light box. That is the diffraction. Yeah, so sorry. It does spread out. So you've got a screen here. Sorry if this isn't very well laid out. But say this is a transparent screen. This here, so the fringes may appear here and they would be like this. A couple of things to know about the single slit. The central maximum is twice as wide as the others. So twice, 2 times as wide. And this is because you've got the constructive interference from the left hand side of the diffraction and the right hand side coming together, so you get 2 times the effects in the central. This is quite an important thing you need to know, and then as it gets further out the fringes become dimmer because it's not diffraction grating as we specified in the other video, and the intensity does go down. This leads us to produce a nice diagram, which I'll draw for you now. You might need... Oh wait, sorry, I've missed out one formula you need to know. So for the width of the middle slit, middle fringe, as I said before, it's twice as wide as the other fringes. So the fringe spacing is only going to be twice as wide. So here's a fringe spacing for a typical fringe. Same one on the side. So it's the wavelength times the diffraction. Oh no, wait. Sorry. D is the distance to the slits. Sorry, I was going off grating. D is the distance to the slit screen distance. So say that is a slit, that is a screen, that is D. And this is the light source going through here, diffracting into the fringes which you see on the screen. So there we go, that is what D is. So that should be D. So you've got D there. A lot of people love the D sign just the way it is. Okay, so you've got over the spacing. Now the spacing is the distance between the fringes, not fringes, the slit difference, yeah? And obviously it says there's a single slit, it's the distance between the two ends of the slit. That is your fringe. For a standard fringe, however, as we said before, the middle fringe is twice as wide, so we times the top bit by 2, we leave the bottom bit unchanged. So the width of a single slit is 2 lambda d over s. And that is it. That is the equation for the diffraction of the single slit. So that is the basic terminology that you need to know. That is basically the maths of that done. Now we go on to the how to explain this in terms of a diagram. So the diagram looks like this. So we've got our standard intensity up here, and then across the bottom we've got 0, and it slowly gets larger, it gets further away. This on the right, this is the right, and this is the left, and this is the central maximum. And now another thing we need to know is that the intensity gets less as you get further away from the central maximum. So it slowly dies down as you get further away, which should be the same on each side. So let's assume we've got a single slit diffraction. We'll do this, we'll do the middle one, which is large, and then slowly gets less and less and less. This is less and less. So if you can't quite work it out, probably because of my rubbish drawing, it slowly gets less and less. It should be the same on each side. Now that is basically the diffraction thing there. They have labelled on the diagram in the book I've got here, they've labelled like 2 lambda d, etc. But I'm not sure you need to know that. So I'm just going to leave it, as you can rewind the video to have a look at the diagram again. But all you need to know is the intensity dies down as you go further away from maximum, and it's twice as wide. That is basically diffraction in a nutshell of a single slit. There's more diffraction of waves, which we'll come on to later when we do the topic of waves. I'm hoping you've enjoyed this DVD, film, YouTube clip. Hope you share it with your friends, and we'll get some good banter going, and enjoy the rest of the series.